Не нужно. Ой-ой-ой. Мне нужна, у меня руки, видишь, какие кривые пошли. Руки кривые с утра пораньше. Yeah, right. Okay, I think it's 9 o'clock. We can start. So, yeah, it's pretty sad that this is the last day of the school. Like I'm really enjoying Nikita providing me various points of reference in his previous talk, and so I can kind of incorporate them into my lectures. So, we will talk about rigidity in a minute, but in Nikita's lectures, one object that was prominently appearing in the last two lectures was a partition, or in fact maybe R tuple. So forgive me if I take, there was an R tuple of partitions lambda, and there was some sort of interaction, and that had to do, this R tuple of partitions lambda had to do with the moduli spaces of bundles, instantons, sheaves, something that live on the plane with two coordinates x1, x2, which a torus was scaling with weights epsilon1, epsilon2. And so at the end of his lecture yesterday, what happened is that a certain defect was introduced along one of the lines, and so then it had to do. But there's also another direction. This all fits inside 4 dimensions very nicely. There's another direction in which one can go, and one can let this object stack. So this will be still kind of epsilon3 direction. And one can let this object stack in this direction. So this will be some partition. Maybe I'll draw, I don't know. Let me draw some simpler partition so that not to worry too much about it. There was some, this was a partition lambda, but now lambda will be this object here. And there will be this 3-dimensional thing, which is, somehow. It's like in Professor Schlossman's lecture, except in his lecture, this thing was growing up, and you can rotate this picture. Does that make sense? So if you slice it, it's a sequence of partitions that each fits inside the other, but eventually they all stabilize in partition lambda. This is supposed to be infinite. This leg is infinite. And R tuple, so one such object by the same argument as we somehow thought about this partition as representing various monomials. These guys here, so this object here, this was really one partition, was a torus fixed point. In the Hilbert scheme of C2 points. Right? By the same argument, if you bring in one more monomial, monomials in one more variable, this would be this whole picture, this 3-dimensional picture. This is ideal corresponds to ideal. Now in the ring of polyelements with 3 variables. But it's not of finite codimension. It misses all the points that go, all monomials that go in this direction. They're all not in the ideal. That clear? So this is ideal. First of all, it's a point in the Hilbert scheme of now curves, right? So what does it mean? It's an object of dimension 1. Complex, it's not the point. It's an object of complex dimension 1. And this particular ideal is this corresponds to some fattening of the x3 axis. Okay. So this is, right? So this goes the equations that define this ideal. The monomials. For example, all monomials of x3, they will be sitting here. There will be this x3, x3 square, x3, 3, and so forth, right? So previously, so these are all functions on the axis itself. And previously they had to terminate, but now they never get into the ideal. So this ideal something of dimension 1. That makes sense? And so an R tuple of this such object is a torus fixed points in more. So R tuple of flat objects, this was a torus fixed point in bundles of rank R on the plane, right? So this is in sheaves. Well, I'll write sheaves of rank R on C3. And as such, it's an object. This belongs to the subject to the field of DT theory. In a sense, DT theory in general has to do the old DT theory has to do with counting things on threefolds. Counting curves on threefolds, counting points on threefolds, counting bundles on threefolds. So this is. And so now, if we form a generating function, except I think it's sacrilegious to denote the elliptic modulus of elliptic curve by a letter other than Q. And so I'd like to keep Q for that. So we need some new variable to count the boxes. So I think I had the variable Z as an argument of Quiver genus, but I think it's maybe we'll use some other variable for that today. So maybe we'll count the boxes. So we count these boxes, count these objects we somehow form. So we write some kind of partition function of a bunch of partitions. So maybe this partition, some other partition, and so our tuple of them. And then we have variables, we may call it Z, maybe T1, T2, or A1, A2, A3. No, this is not. A C1, C2, C3, and then A1, so forth, AR. This is this is an R tuple of partitions. And then this is the where this variables, like in Nikita lecture, they're assigned to this, the assigned position the same exact same way. These are the weights. I think you denote Q1, Q2, Q3. So I think the notation in Nikita's lecture, Q with a cross. This is Q with 1. This is Q with 2, and this is Q with 3. Well, right, but anyhow, I want Q to be to be parameter elliptic curve. So with all due respect, I will not use this notation when everything is Q with some decoration. Right? The parameter of the elliptic curve, that's for, well, anyhow, yeah, we'll talk about it. What? Yes. Anyhow, so that what I was gonna say. So this is this is function with the weight when you sum. What do we say? We sum with some z to the volume. And the volume you have to, of course, the volume of this is infinite, but if you subtract the cylinder, if you subtract the cylinder over partition, the volume is finite, so you can make sense. And then there's some, stuff. Just the natural analog, if you can imagine, it's a natural analog of what you saw before. We'll talk about it in a second. And then that's a very interesting function. It depends what? So R tuple of partitions is an element, so this is this whole thing, is an element in a product of Fock spaces. So because partition is the base of Fock space, so it will maybe an element in some Fock space. And since the parameter A1 is attached to the first partition, I write A1 tensor Fock space with the parameter A2. And will be a Fock space with the parameter A3. And it's, like I said, it's very, very interesting what this function is, even for one. So in Nikita's situation, if you had one partition, it was not a very interesting function. Here, even for one partition, it's already a very interesting function.
Maybe you have AR, otherwise
AR, right. Thank you. AR. And this object, so what is this? This is a solution. And now my choice of variables will come to haunt me. I'll write QKZ, but this Q is T3. For what? For the real, for something like you take U, H bar, where H bar is, well, depending on your notation, is more or less T1 times T2 of double loops into GL1 double loops. And now I have to explain, since it's my lectures are supposed to be, somehow I'm supposed to explain things. I have to explain with all, where is the father of QKZ? Okay, in his absence, I will explain what this equation is. So QKZ is maybe one of the, and so there's associated with QKZ, there's some other system of difference equation, which is also very important, and the corresponding dynamical equations. in the variable z. So what is QKZ? So if you write QKZ in its full glory, it will take many, many pages, even the simplest example. But if you write it represented graphically, it can be. So in fact, Pasha Yesengrov likes to say that QKZ is the definition of QKZ is the equation that cannot be written on a single page of an Ocidi-Gladek page. But if you do it pictorially, you can write it. So what are the ingredients in QKZ? In QKZ, you need two vector spaces with labels, and you need associated to these two vector spaces, you need an operator, maybe V1 of A1, V2 of A2, and you have an operator from their tensor product to their tensor product. Okay, that's called the R matrix. So this is called R matrix. And now imagine we have a cylinder. And we have some of these strands. So we have some collection of representation, VA1, VA2, and so forth. VAR, some collection of representation with V1, V2, VR. They don't have to be the same. And all of them, except for one, are innocent bystanders. So they all just, nothing happens to them. Well, this one of them, in this case the second, that makes, so when you write R matrices, this thing is oriented. May have further symmetries that allows you to somehow change orientation, but it is oriented. It's so this go straight, nothing happens to them, but one of them makes the tour of the world, goes through, and then comes back here. Clear? This would mean what? This means I act by the R matrix. You know, every time I have a cross, I act by an R matrix, and so this would be a product. This is a product. What's written here is a product of R minus 1 R matrices. And now, in life or in experimental physics, anytime you have a cylinder, you know, if you go around something, it may not be quite periodic. You know, you may come back not quite the same person as you were at the beginning. Maybe wiser, maybe you learn something, maybe not. So this is to say that in any system like this, you're allowed to have another operator that tells you what happens to your space as it crosses this line. There's some kind of operator that you're allowed to cross the line. So maybe I don't need a name for this operator right now. But what I do need is I need this operator. So my R matrices always enter this cut from this side. So what I need to be able to do is I need to be able to bring, I need kind of like a Young-Baxter equation, but this says you can bring this crossing from before or after. Right? So this is to say, acting in the tensor product of two representations, this operator commutes with the R matrix. Okay? And so what's an example of such operator? The R matrix in general could be arbitrary function. But in our situation, it will be a function only of the ratio. So as an example of such operator, you can take, for instance, you can make this operator to be a shift. So you had some, right? So this is, yeah, it's just right. So if I put like that, so this is my V1 of A or V of A. This is an, what is this? This is a function of A with values in V. Well, I can shift it. The difference operator. Right? So since the matrix depends only on the differences, this is written a difference operator. And also I can act by any element. I can act by any element. I'll write Z capital. This is representation. This is representation of some quantum group. So I can act by some element. And what I require from this element, the condition. So I require that my have this depends only on the ratio. So this shift commute. And now if I want to have this expression, well, that means Z tensor Z has to commute with the R matrix. Right? So what are the elements that commute with the R matrix? So if you think about in a quantum group, well, if you don't know what a quantum group is, no problem. I'll explain it in a second. Well, I'll try to explain it in a second. But the elements, there are not so many elements in the group that satisfy this condition. But there's, so for example, you can take element from Z could be element in the Cartan subgroup. Cartan subgroup. Kind of like the maximal torus. So if quantum group has the maximal torus, and an element in the maximal torus satisfies this condition. And this group here, well, its maximal torus is in some sense one-dimensional. Somehow think about it. This is in the end, one by one matrices up to some loops and so forth. This is really one element here. In the Z, for us, Z, the big Z, little z in the Cartan, this is an element in the Cartan subgroup of this UH bar GL1 at head acts by roughly Z to the volume. So it acts in, this is a grading operator. And how it acts in a Fock space, it acts multiply this element by Z to this volume. So this is how the variable Z enters this equation. Yeah, exactly. Exactly, yeah. Right, so now we have, so this group depends on parameters T1, T2. T3 is the step. A1s are the points where I have my Fock spaces. And Z is the element Cartan. So we have now explanation for every single variable in this formula. And now, if you think about it, like for instance, well, what does it say? If you unravel this equation, this Q is QKZ.
Can I ask you a question real quick?
Maybe, yeah. If I can understand it.
Yeah. So this, in your picture, these terms are set theoretically only supported on epsilon 3 axis, but not the other two, right? Only one axis.
Right.
Okay.
Yeah. Oh, good. That was good audio. So if you write this equation in its full glory, well, so in general, so this is somehow in general a Q difference equation, a linear Q difference equation. equation has the form, is of the form that I have some. So this is some vector in some space. So I have some vector z. Maybe that was a bad idea to denote this partition function z, but maybe too late. Maybe call it. Let's call it. There's too many z's otherwise. Let's call it capital. We did use this thing, so let's call it psi. That like a wave function. That. So. Psi of, so what's going to happen? We shift some a, some kind of, in this case we take a2 and we shift it by a1, and we put q a2, and this, like I said, q is t3. And then a3, and then whatever, all variables. This means you apply some kind of matrix that depends on all variables to this element psi of a1, a2, a3. Right? So I shift by, so actual geometric shift is by T3, but I don't want to consider T3 difference equations. I want to say Q difference equation. And so geometrically, what happens? Geometrically, this is an integral, some kind of, some kind of push for some kind of genus of some space. Some genus of some space. Or not, union space. Some kind of disjoint union spaces. And then we form generating, when we take the generating function, we sum them up, sum with z to the volume. Right? So z things with different volume belong to different moduli spaces, so we just sum up over that kind of data. That makes sense, right? So this moduli space has connected component corresponding to degree of the curve. The degree of the curve is fixed by the size of these partitions, and then further by the volume of this object. So this, like in Nikita's case, partitions of different size, they belong to different moduli spaces. And what happens here is these spaces break up. So the space break up, and you get this computation. So you have some genus of some space. You can break this space in pieces, and you find some relation of that kind. Now we had many computations. This is a very complicated spaces, but we had many computations of that kind, where you can imagine there's break the space, you can compute the genus. But so if you look here, so this in principle, so if you think of this matrix, this in principle be an object of the same nature. You have a countably many spaces, and you sum them up, sum the contribution, all of them up with some parameter, which is like that. But if you look at QKZ, the matrix elements of QKZ, these are QKZ equations are monomial in Z. Z is a diagonal matrix with monomial eigenvalues. So so in this equation, you multiply by diagonal matrix. Right? So this means every matrix element is going to be monomial in Z. Just extremely remarkable statement. What means in this computation, a million quadrillion thing has to be equal to 0 for this to be true. Is that what I'm trying to say? So suppose you have let me say it one more time. So this object is some series in Z. This object some series in Z. If you write the ratio, you expect this series to be the rate, say, right, one matrix series, the other matrix series. Divide by another, you expect this to be series. But in fact, it's a monomial. No, every matrix coefficient is a monomial. Means some extremely strong statement. So, yes, please. This is a vector valued function. But if you take, this is instead of a vector valued function, you can take the corresponding fundamental solution, it will be a matrix valued function. And then if you have two fundamental solutions, you can, if you have a fundamental solution, you can find the coefficient matrix of your equation by just, taking this matrix and multiplying by the inverse of that matrix. And so you have two things which are series, matrices of form a series, take the ratio, they're monomials. That make sense? But whatever the R matrix, if you write it in this form, every matrix coefficient is monomial. Which is, in QKZ, maybe you don't appreciate this fact, but if you think of geometric interpretation, that's an extremely remarkable fact. Yeah. Say it again? Right, but is some it's some kind of grading operator, right? This is like in conformal field theory, it's like z z is like z to the L naught. Yeah, so this is some kind of grading operator that acts in like normal somehow usual base, it acts diagonal, right? Means when you multiply the matrix, and it's going to look, this will be monomial. Yeah, exactly, yeah. Yeah, I mean, it's in KZ, it's obvious. No, in KZ, it's an obvious feature. It's just some conservation law. But the fact if you write it geometrically, it means a lot of vanishing. And this vanishing, so this kind of the vanishing is kind of the key. The vanishing, this vanishing is super important. Because it's, so people say when they count like actual, when you count objects like this, people say they do some quantum algebraic geometry. They count curves. Right? Well, I don't mean it's an honorable thing. I mean, I'm not saying just mean the word quantum is so overused. Yeah, but somehow you really count things, and that means there's like the simplest contribution, then the next contribution, then the next contribution. But here, if you look at this expression, it's only the lowest contribution, only kind of like the constant things contribute. Okay? So this means this vanishing means your quantum contribution is in fact classical. Yeah. No. No, that's not length space and it's not central charge. So, and this comes, so in other words, you're doing some quantum computation in the sense of algebraic geometry. You somehow, sum over somehow non-trivial curves somewhere. But in the end, it's only the trivial ones, kind of the constant math contribute. So this vanishing. This comes from rigidity. You have to use rigidity. And it's kind the use of rigidity here is the key thing. So this is like where the kind of rigidity idea is. Now what sort of rigidity can we use here? So this rigidity, I remind you, so this is for this kind of a T here, it's a Bruch rigidity. in K theory is always okay. For any kind of manifold. And so in K theory this works, it works in homology, works in K theory beautifully. In elliptic homology this is not, it's not going to be like that, because so in elliptic homology what you need is so this is, so in K theory, so this computation is why this computation totally works. Works for some construction. I didn't tell you what's the R matrix yet, right? So because it's easy to say let R be an operator, but then you have to say something about what that is the operator for some construction of the R matrix. And then if we have, hopefully I'll have time to say something about the construction of this R matrix. And so Quiver rigidity requires what? Requires, oh, it's okay. I was explaining the what's QKZ, so now we can all applaud the inventor. So Quiver rigidity requires what? Requires C1 to be 0, or some number n to divide C1, and then this parameter and parameter, whatever the parameter there is, maybe to the power n b1. Right? So this is, so already in Nikita's lecture yesterday you saw that it's better to think that I'm not kind of applying Quiver genus to some moduli space, but I'm sort of integrating one on some derived moduli space. Right? And so that this is already in Nikita's lecture. The moduli space was smooth, but he put a cotangent bundle on it, and then it became. And then if you think of this as a derived object, then it's something zero-dimensional, and you're computing its fundamental class. And in this case, well, for this sort of modulus we're considering here, that's unavoidable. So if I have my moduli problem, and the tangent space to that will not be some actual, this is not an actual vector space. It's like because this will be some, so in Nikita's situation, we had a smooth manifold and it had a tangent bundle. In this situation, it's a singular object. It doesn't really have a tangent bundle, a cotangent bundle separately, but it has their differences. So this has two terms, so there's some deformations. And then there'll be some abstractions. And in Nikita's lecture already, we had this situation when, or in general, Quiver genus is what? You have some bundle. If you have a bundle over any bundle or any sheaf over any manifold, always has an automorphism. You can, if it's a linear object, you can scale it. And so there was this parameter, maybe, what do you say? What are we going to call it? It has to do with the canonical class of C3. So since it has to do with the canonical class, maybe let's call it kappa. Is that? Because if I write k, this will be confusing with many other k. So this is this kappa. So this is my parameter. This is like the parameter of Quiver genus times deformations, but there's time abstractions, but they're in this situation. This is the dual. Dual. The space is just like Nikita considered, except it's not separately something this and this. It's the difference is defined. And this is the parameter which is in real life in our particular situation is T1, T2, T3, because that's the canonical class. Has to do with the canonical class. What? Yes, right. or in this case C3. In general, if I have some threefold, that will have some canonical class. And this, right? And so now we'll look at it, and we see that the first Chern class of that, what's it going to be? It's going to be the first Chern class of that minus the first minus the first Chern class of that. So it will be two times the first, whatever. If you can define this, there's no bundle like that. But if there was a bundle, there will be twice the first Chern class of deformations. And with Nikita, we actually proved that this is, you can't, this is defined. There is this bundle does have a square root. And so, in particular, it's not equal to 0, but is divisible by 2. Right? So you can't really do full-fledged Krichet genus for these spaces, but you can have a situation when kappa square is 1, then you can have this. This is what Henry, for those of you who remember what Henry's lecture, so there he was talking about how people in kind of Duns and Thomas theory now explore the properties of this Krichet genus. Unfortunately for this, you have to have that condition. No, there's nothing else. So we will, since you lose a variable here, you lose a variable here. Maybe we will focus on K. Any questions? But in this space, this is certainly not equal to 0. It's certainly not equal to 0. So in Nikita's situation, his modular space to begin with was symplectic. In particular, its first Chern class is 0. No, for this original modular space, this one is symplectic. For this, so this guy. It's even better, it's symplectic. So in particular, first Chern class. So you can have a very meaningful theory of Krichet genera for that. If you want to do it in one dimension up, then you have to do this kind of Krichet genus at -1 called the Witten genus. So you have to do the Witten genus. Yeah, something happened. Namely, something happened that this one is not 0 there for the modular space. Right. So this is just connect with Henry's talk, and there's some kind of doing elliptic genera in this situation for Duns and Thomas theory. This is active field of research. I'm not going to say this. I'm going to talk about the rest of the lecture. I want to talk about how they actually construct our metrics. Yeah. In the central board, I was explaining that QKZ has a very remarkable property. From the point of view, if you think of this is supposed to somehow reflect some geometrical problem, the fact that this quantum variable z enters only monomially, it's an extremely remarkable property. You need to have you have to have almost everything vanish. And this vanishing is proven, before you prove something is 0, you have to prove it's a constant. And this is, once you know some complicated expression is a constant, it's then easy to show. It's sometimes very easy to see it's 0 because you can, in some limit, you can show it's 0.
Why you need GL1 you can directly use quantum groups, right?
That is a quantum group. It's a quantum group. No. What do you mean G? Which G? It is a quantum group. It's just the quantum group is directly connected to itself. It's not related to the fact that there's double loops here is important because No, but they will not solve this problem. This problem has a unique solution. You know, the other R matrix, if you ask for, if something solves QKZ for one R matrix, it's not going to solve QKZ for some other R matrix. Right? Because for the reason that if you know solution, you know what the matrix of the equation is. Right? So there's a yeah. Uh-huh. That's right. It's like if already we were discussing before you came that how sometimes people denote everything by Q with different decorations, but today I tried to somehow because it's particularly confusing in QKZ because in QKZ you think that a lot of people like to study QKZ on level 1, in which case the shift Q, it's a Q difference equation, the shift Q and the quantum group parameter are related. Same variable. But in principle, in QKZ, there's no relation between them. Just Q in QKZ is a free variable. No. For a given quantum group, you can study QKZ with arbitrary Q. But that relation between the deformation parameter and that Q will happen if you impose level conditions. Anyhow, I just say for people, it's extremely confusing to denote everything by Q, and it's particularly confusing in the context of QKZ. Because I think the Q difference equation should be a Q difference equation, all the other variables unrelated to that Q have to bear different names. All right, so now the R matrix. R matrix is the beginning of a kind of a old story or long story. So R matrix is something like that. Right? More, what's this? This is, well, if you think of quantum field theory, two particles with internal degrees of freedom in two spaces V1 came together, boom, and then it came out, right? Which is to say that there's a more fundamental operator, namely when they come together and then boom happens, and then composed with this boom decaying into things. That clear? So this is where this is. In fact, this operator is just the transpose of this operator. Right? What? That's right. That's right. And so geometrically, this Fock space here. What is this Fock space? This Fock space it's some module over this group. Well, what it is equivalent K theory of the Hilbert scheme of points. Right? And more generally, if we want the R-fold tensor product, that's equivalent K theory of sheaves of rank R. So this operator is supposed to be, I take equivalent K theory of sheaves of some, so I'll write M R1. So these are sheaves of rank 1. Or bundles, sheaves, bundles on P2 of rank R1. Tensor equivalent K theory of M R2. And this has to go to equivalent K theory of M R1 plus R2. There is a way to do this operation so that really nothing happens, no boom boom. You just take two objects and you take their direct sum. This is like saying, this particle and this particle, they thought they're going to interact, but in fact they didn't see each other. Right? They just, you take direct sum and then you undo the direct sum. Nothing happens. So you need to have something. You need some kind of, this map has to be somehow non-trivial. And to explain how this is constructed, maybe so what is the locus? So maybe I'll say, if I take, there is a product of MR1 cross MR2 really does embed into MR1 plus R2 as locus of direct sums. And what does it mean, direct sums? Direct sums means you just take two things, take two bundles, and form their direct sum. Right? What does it mean, this direct sum? This means these are things that are fixed. This means fixed by the action. So this is, again, like in Nikita's lecture yesterday. So on MR, you think there's an action of GLR. But in fact, the diagonal acts kind of trivially. Well, acts in a non-interesting way. Well, I keep saying it's very interesting that on every sheaf, I have a scaling action. But this means on the moduli of sheaves, every sheaf is fixed by the scale. So this is fixed. But if you scale one separate the other, this is non-trivial. So if I take, matrix of the form U, 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 and then 1, 1, 1. So this is a one-dimensional subtorus inside my diagonal matrices with A1 through whatever, so forth, A1, A2, so forth. So this is a fixed locus of this group, which you can also say that what does it mean fixed by a torus? It means, i.e. the same as critical points of the moment map. For this group. This action has a moment map, and something is fixed if it's a critical point, and some kind of energy, and this is if it's a stationary point, and so maybe we'll just talk a little bit abstractly about critical points. Many spaces. So, mathematical physics, some people are somehow ambitious to study actual dynamics. More modest people like I, most of the time study just equilibrium, just the things which are just the minimum of some energy. So many spaces in physics are critical points of some function. What? Where? So we did both. No, but this partition function had a boundary condition. The boundary condition lives on the plane. So you count something in C3, and your boundary condition at infinity. At infinity of C2 is the plane. At infinity of C3, there is a plane C2. And that's so. As a function of the boundary condition, we're doing partition function inside. So we describe the things inside via difference equation that satisfies function in boundary condition. That makes sense? So, like I said, many spaces in interest of mathematical physics, they're naturally defined as critical also of some function. Maybe right? So this is if you have a function that has in particular, to functions, whatever defines your critical locus, you can also add one more function to be the moment map of some torus action. What such terms are called? They're called twisted masses, is that, or something? Something like that, right? Equivalent parameters, yeah. You add twisted mass. You kind of add, you get, right? You add a kinetic energy of some kind of for some kind of rotation. And then you have, suppose I had some, so maybe I'll just draw a model situation, just kind of to be pointing to something. So you can have a situation where for special values of parameter, the critical locus will suddenly jump. This is so maybe let's consider a model situation. You had a function, maybe something your function. So this is a U abusing notation. Maybe I take U to be an element in the Lie, because moment map goes to Lie algebra, to the dual of Lie algebra. So maybe U will be an element in the Lie algebra. So I'll write U times something, whatever, x1. So this usually absolute values with some. So it's like absolute value. Typical moment map looks like this. Times, again, absolute value of x1 squared minus the absolute value of x2 squared. That sort of thing. Some coordinates on your space. I mean, a torus acts on some space. And right now we have an abstract discussion about torus acting on some space. and so in that situation we can add the moment map to whatever the critical locus was. And so then I'll have so if a function will look something like that. And then this is for, so maybe, sorry, this is for U bigger than 0. This will look like that. For U equal to 0, it becomes flat. And for U less than 0, it curls in the opposite direction. And so you want to have a map from here to there going through here. So this is from we want to K theory of the fixed set. Fixed locus to K theory of the ambient space. And then this kind of transpose. I'll just write it. Have this map, and I transpose goes the other direction. K theory of the fixed locus. I said nothing so far. I've just said that we want this kind of map. But if you want the physical interpretation of that map, you may think about it as I had some term in the potential that changes sign, and my critical locus, all of a sudden there's a change. What was the minimum became maximum, and what was maximum become minimum. Right? Well, you think exactly. Then you get, if you go, this whole decomposition of this would be the R matrix. All right. And so physically, it's it's pretty clear what sort of thing you should consider. That if you should consider you know, what could be if you have, if you're in this equilibrium position, you know, you maybe you have your ball, there's some kind of ball here sitting. Well, of course, this ball can roll down. Right? And so you should think of this map, what's it going to look like? It's going to go to, you know, I'm going to kind of map the point here to all points where it can roll down. Somehow, in terms of K-theories, you'd say like this: there's a attracting manifold, or whatever, downslope manifold. How do we say? What's the word for this kind of descending manifold? Is that called it's called descending manifold? Yes. Yeah, somehow descending manifold. And the descending manifold, it projects to the fixed locus, because, you know, by definition, descending manifold is something that grows at a fixed locus. So then you know where's the, you know, stable manifold. Exactly. Yeah. So this is a project. There's a natural projection. So this is projection. And this is inclusion. So you can think that you would like to maybe, in terms of K-theory, the kind of map, so maybe projection P, inclusion iota. You would say, well, let's say I do P pull back, iota push forward. Something like that. It's not the actual formula, but otherwise it'd be kind of simple if it was the actual formula. So what's the both geometric and mathematical difficulty with this definition, and the physical and geometric and physical difficulty with the definition, is this descending manifold, this stable manifold. It's not closed in the ambient space. This is not a closed inclusion. There's no push forward here, really, because it's kind of locally closed. But if I let this ball roll, if it rolls, it might very well roll to a different position, a different stable such configuration. It will roll down to some other position. You can have this kind of Morse trajectory, soliton, something, right? So that's, in other words, this guy here, what I'm trying to say, this guy here, this is not closed. And those of you who went to the exercises, we looked at the simplest examples of this sort of things. The simple examples of this kind of things are like Schubert cells. You know, Schubert cells, it starts as stable manifold for something, and then if you close it, then, you know, stuff happens. Who knows what's in the closure? What this thing looks in the closure? And in general, in algebraic geometry, it's okay to take the closure for abstract reasoning, but not in any concrete situation, because you never know what's in the closure. Right? And you don't. And even if you knew what's in the closure, that would be something horribly singular. It will not have, you know, somehow, will not. This would not be a nice map. Instead, the best way to deal with this issue is the following. So this is, you can explain in, historical, you can explain explain this in why you come to such definitions. Maybe there's some kind of historical explanation, but it may be easier to just start from the end. Starting from the end, the exact same thing we can write in elliptic homology. So we can think of elliptic homology of fixed locus you want to start with go to elliptic homology of ambient space. This is what? So we don't this is elliptic homology, like I said, this is maybe this notation is slightly misleading. Because there's no elliptic homology ring. What we would like to say, from this is a map from line bundle here to line bundle here. So this is a section. So this thing is a section of some line bundle. In fact, some theta bundle. Some theta bundle. Because push forward, push forward involves theta bundle, so it's a section, some line, some kind of theta bundle. Theta bundle, which we know near one fixed point, one component, of the fixed locus. And wish to extend. Yeah, because a sheaf of rings is not a ring. So this is not it's not so particular abstract. This is not so super abstract, because remember we had this picture. Yes, I'm not going to try to redraw the picture from yesterday, but maybe schematically redraw it. Remember what was for instance, we would look at elliptic homology, equivariant elliptic homology of, say, I don't know, let's say P, what would you have? P2 or Pn. What was that? That had some variables. A. And so this is, and over this is elliptic homology of a point. And then a bunch of, I draw them as linear subspaces, but they're they are abelian varieties, so they look something like that. Given by the equation that this variable t is equal to one of the ai's. And they intersect where this A it over. So maybe when this was, maybe let's say there's a T equals maybe A0 inverse here T equals AI inverse, here T equals AJ inverse, and then where AI is equal AJ, these two things intersect. That makes sense? So suppose we start at the top. At the top, we know so maybe this is, so in our projective space has n, so maybe n plus 1 fixed point. This was where T equals A not inverse. This is T equals A1 inverse. And the attracting order is going this way. So suppose we start at the top. At the top, here, we start here. And here is here we know. Here, we just look this at iota push forward to p pull back. Section of some line bundle. Now, suppose we come, so we come to the, and right. So then we come to the, next fixed point. Maybe we come to some other fixed point. Then we do them in order. We come to the next fixed point. Then there we're supposed to reconstruct a section of some line bundle from what? So we come to, let's say we come to the second one. So let's say T equals A1 inverse. Here, what do we know? It's a section of some line bundle which we already know, or the intersection with the first one. And we know also a little bit more about it. So we know that we also know, right. This is supported. This is section some line, but more importantly, supported. This is important. Supported on full stable, full attracting locus. So this is, maybe we should think of this as seating. This is, to make things symplectic, maybe we should think of this as seating inside of its cotangent bundle. This would be. And so we start with something which was supported. So we start with a section that was supported. So it's always right. In this picture, I kind of assume, the fact that the attracting and repelling, they always balance, kind of assumes in this discussion that there's something like a symplectic thing going on. So we started with a section which was already supported on Pn itself. So that says about this section on the next thing we know what it equals at this point, and we also know, so we know the value. Know the value here. Here by induction, and know some vanishing. Plus vanishing from support. Condition. So if you if you know enough about a section of a line bundle on the abelian variety, you reconstruct it uniquely. And makes sense? What? Well, it's normalized there. So what? No. This has nothing to do with the R matrix. This is spaces of some dimension. They're not lines. Yeah. This is schematic representation of the kind of picture that we had. This picture that was here for half of yesterday's lecture. A bunch of linear subspaces that intersect in some condition. So what is it? Somehow, just completely abstractly. Suppose I have. What would you like for an arbitrary algebraic variety? What would you like a letter for an algebraic variety? What? V. No, that's a vector bundle. Let's call Y. Let's call Y. So Y is algebraic variety. And L line bundle. D. So these things. So this is a codimension 1 condition. The things intersect in codimension 1. So this is D divisor. So you look at sections on your Y of your line bundle L. You can restrict them to the divisor. And so this is to the divisor line bundle L. And there is what vanish under this map what vanish under this map? This is sections of the line bundle that vanish on the divisor. So these are the sections of the Y, the line bundle shifted by the divisor. Done. And then this may not be surjective. There, in principle, could be a connecting map to H1. So forth. Now, what does it mean what does it mean interpolation problem? Interpolation problem is reversing this error. Right? You have a section defined on the divisor. You would like to lift it to section defined on the whole variety. Right? So you have a polynomial in two variables, which you know when it's restricted to a curve. Then you have to reconstruct, you're trying to reconstruct the polynomial to variables from its restriction to a curve. Right? So you're trying to reverse this map. So the co-kernel of this map, so this kernel of this map has this, goes here. So these are abstractions to interpolation. And this is, of course, and this thing is ambiguity in interpolation. Right? Because if you have some section just vanishes on the divisor, it'll just go to 0, right? So to have a unique solution of interpolation problem, you would like this group. You would like this group to vanish. So how to say? This is mathematical notation that you would like this to happen. And you would like this to happen. Right, so if these two things happens, then the interpolation has unique solution. It may still be, this. I mean, if this is not zero, then it never has a unique solution. But this, there's this thing. Well, anyhow, there may be a unique solution even if the group's non-zero. But somehow, we would like this condition. Now. No. This is not what we're going to do. We're going to do something else. So we will, in the exercises, I don't think you guys got to that part yesterday, but in exercises, one has to prove that if I have an R for R case, so for us, Y is an abelian variety. Product of elliptic curves, but what I'm going to say is true for any abelian variety. So L and Z, well, they're line bundles, some kind of theta bundles, both some kind of thetas. What we're going to use? We're going to use that if the degree of D, or the degree of the line bundle. So what we would like? We would like the degree of L minus D to be 0. If this line bundle has degree 0, which is not a numerical condition, it's a condition. So if a product of n elliptic curve, then it's like n choose two conditions. Because again, in exercises, somehow line bundles on the product of elliptic curves are parameterized by symmetric matrices. And this condition, this is some sort of some kind of this is some kind of balance. This is some kind of balance that comes from, in these applications, come from symplectic form. On your original variety, we had some original variety, maybe call it X. So if I have a degree 0 line bundle elliptic curve, there's a dichotomy. So then there's two possibilities. Either L minus D is trivial, or cohomology of every single cohomology group of this thing is 0. So this is something so I don't think we're going to get to that in exercises, but you can, there's in exercises, you can work through them, you can prove this. And so this looks good. Except, so this would say that this probably will have unique solution most of the time, except we have to worry about the situation. This is some kind of resonance. That we have to avoid. And that resonance you see in these formulas. In every single formula, like well, not every, almost every lecture in this workshop has to have this formula. You look theta of x times z over theta of x times theta of z. What is this formula? This formula is this is a formula. This is interpolation of the function 1 from zero elliptic curve to the whole elliptic curve. Right? You're looking for a problem. You have a function 1 at the origin. You would like to find a section of a line bundle of degrees, a section of suitable line bundle that, or from 1. Section of certain line bundle that interpolates this. But you see in this formula there's a denominator. Right? So there's this guy here. So it means, and this is why, because if I have a trivial line bundle, then something else happens. That makes sense? And so this is, you need some variable like so. So if you're solving interpolation problem, so in other words, if you're solving interpolation problem for fixed line bundle, you may very well be in trouble because it may be the case that if you come down sufficiently far away, you're going to hit a resonance. You're going to hit a pole, and then you'll be dividing by 0. But if you, from the beginning, from this problem, you introduce this variable z, so make this line bundle vary. So whatever line bundle you have, you can vary it. So your original line bundle from the very beginning, from here. Instead of solving it for fixed line bundle, you can solve them from all line bundles at the same time. You can think of this as you can twist by an arbitrary degree 0 line bundle, because if I twist everything by an arbitrary degree 0 line bundle, nothing is going to change. So I take peak 0 of the elliptic homology. Well, who knows what this is, but it always has, there's always subset here. There's always subset here, which is formed by first Chern classes of line bundles. So there's always peak of x itself tensor your elliptic curve. This comes from the, if I have a line bundle, it has a first Chern class. If that first Chern class, I can make a degree 0 line bundle. Okay? And so here you introduce this variable z here. In this variable z, these are the dynamical variables. In the quantum group, in the quantum group language. Groups. And also, right, everything's. And also, there's the same z. The z come from peak of x. Also the z, so this is also z from kind of this kind of z volume. People call them scalar. And then they demonstrate their full glory if, well, I have 1 minute. So this is, maybe I'll try to say what I was saying one more time, and then I just say where are you going to see the z come back? Is that this is, we introduce at this stage, we introduce them so that not to worry about poles. Because if I multiply by generic degree zero line bundle, then the whole thing works through, and it's just like that Z over there. But where is it gonna? So they come back if I want to know. I had this function psi of a bunch of partitions, kind of elements. So it's an element in fork tensor, fork tensor, fork. I'll just write inside fork R-fold present, R-fold tether product, depending on the variable A1 through AR, T1, T2, T3, Z. This was solving QKZ, but from geometric considerations, I can also say, I can not just say it solves QKZ, I can make the solution more explicit. I can say, well, it's in fact an integral of something, some kind of rational expression, rational function, times elliptic function, times a product of some kind of Q gamma over Q gamma. And the meaning in conventional language of QKZ, this is the off-shell beta function. Beta. This is like in Collis. Well, we're going through various Collis seminal papers. This what produce you the beta equations. This is the Atawara of the beta equations. And this, you think, what good it is to have an elliptic function here? Because elliptic function is something which is Q constant, right? So this is the analog. So instead of you solving a Q difference equation, then you can stick elliptic function under the integration sign. This is the analog of contour of integration. Integration. You don't have to move. So usually when trying to solve equation, you kind of choose different contours of integration. If you solve a Q difference equation, this amounts to just, you can stick an elliptic function here. Right? And so this comes from UH bar, whatever, G hat. This is from the elliptic thing. Elliptic quantum group, which you can construct the same way. And the point is that you're solving an equation depends on Z. So in this expression, this elliptic quantum group, you have to have those variables. So these variables that are this is the Z to the volume Kähler variables here. They somehow have to come here. And the way they come here is that here they just label elements in peak 0. Okay, so with this, there's some variables, so product. No, that's okay. So how would you like the integration variables to be called? Who knows? Phi. Okay. Phi. I wanted the absolute value to be 1. Oh yeah, okay. I know, no. I write d hard and integral over maximal torus and gauge group. No, you start, so you construct this moduli spaces as quotients of something. And so that's the maximal torus there. Similar, yeah. All right. So it's somehow. At the beginning, it feels like 5 lectures is a lot of time, but at the end, it maybe feels like, okay, anyhow. Yeah. What? Well, in our case, this G hat is GL1 double loops. But in general, there's some kind of G for which you take hat. And I mean, there are many, many ways to explain why if you try to define an elliptic quantum group, you need more variables. Many ways to say it. But in this formulation, I gave you at least two. So one of them, because they have to come up somewhere where you, on the one hand, should. Well, anyhow, I'm just repeating myself. Maybe I'll stop here.
Any quick questions for Andrei? Remember, we will have whole 2 hours of exercises and discussions after lunch, but
Right. And exercises. Maybe once. Yeah.
coffee break.
Раз, два, три. Okay. Нет, нет, я просто пишу, чтобы не забыть.
Okay. Few very quick organizational announcements. First one is we put closing remarks on the schedule, and I suspect that probably not very many people will show up for closing remarks. So we will stay for maybe 2 extra minutes after Nikita's lecture to officially say thank you, and the closing remarks after lunch or after whenever after exercises, we'll just extend the exercises, problem solving, and informal discussions part. Okay, and we have the last lecture of the workshop and the last lecture of Nikita's course.
So our goal in this lecture course is to connect the two stories, the story of enumeration of instantons or integration of modular spaces of sheaves, and the story of integrable systems, quantum integral systems, classical integral systems. And it's a big, both stories are very rich and vast, so I only touched on maybe some aspects of those. But I want to connect them today, and my goal would be to arrive at this blackboard with at least with understanding of the origin of Lux operators of integral systems from the geometry of modular spaces of instantons and their generalizations. Before we do that, I want to comment and maybe explain why these observables, which we introduced yesterday, or the day before yesterday, why they were called Quiver characters, and so why they're characters. And that will, so one way to illustrate it is to generalize the problem and these observables, and that in such a way that the classical Lie algebras and the root systems associated with simple Lie algebras will appear, and then these observables will be indeed related to the characters of the mental representations of the Lie algebras. In particular, Coley asked me at some point, how does it work for other root systems? So I just want to sketch the construction, and it will be useful also in understanding some aspects of this relation. So, okay. So what were we doing yesterday? So yesterday we said that we were studying some kind of enumerative problem, which by localization became a statistical mechanical problem for, and the problem originally was computing some integrals over the modular space of sheaves, and the sheaves were living on a two-dimensional, complex two-dimensional plane, which I called C212. And I mentioned several times, and in Andrei's lecture, you heard today that it is actually we should think of this C2 is sitting inside a four-dimensional complex manifold, in fact, Calabi-Yau fourfold, which is locally a four-plane with coordinates 1, 2, 3, 4. And so there is a transverse, there's some transverse space which intersects with our plane only at one point. And so that plane was C234. So then yesterday we started playing with this problem and introduced the defect, which was, so the defect was obtained by performing an orbifold, which was acting inside a two-dimensional plane, which was and so we had an orbifold in this space, so that when you observe it from the blue point of view, you only see that something is happening along a line, along a complex curve, or along a two real dimensional surface, and so that looks like a surface defect to the observer who is attached to that plane. So he sees just a surface defect. But of course, to the observer who looks at it from from beyond, right? Who sees it as a two complex dimensional object. So I want to be gender neutral. So, but now when you look at it, you can ask, but why did we do this? Why only C2-4 plane? Why couldn't we do some kind of orbifold in, let's say, 3-4 plane? And what will the again the Earth observer living on this plane of reality will see? And so let's do that. So let's. So let me redraw that picture. Again, this is C212, and so we have some rank n sheaves, or for physicists, UN instantons. And now I have the transverse complex two-dimensional plane, and I want to modify this geometry in such a way that the observer who lives here doesn't see anything at all. So for this observer, the world is flat and carried on the three turtles, and so everything is nice and quiet. But the transverse space is modified, and so let me modify it by introducing some group gamma, which will act here and introduce some kind of orbifold structure. And so what are the natural groups? Well, because of various considerations of supersymmetry or maybe symplectic structure for algebraic geometry, it is natural to take the group gamma to be a subgroup of SU2, or SL2 for algebraists. And there is an ADE choice of these subgroups. but let me not kill you with the. No, there is no. So I see. So this guy sees world is flat. No defects. No, here the world was not flat because it was a surface defect. So something was going on along the two-dimensional surface. There was some, there is some bump on the road. But here nothing is happening. It's
What was the reason that you're thinking about them as an ideal shift, but not other sorts of shifts? You could have rank n shifts which are not.
no, you do no. Of course, no. This you look at all rank and torsion-free shifts.
Okay, but then when you integrate over that much, right?
It's just localization because you have the framing at infinity and you localize with respect to the maximal torus of the framing.
But when you localize for a fixed locus of that much, right? Is it always written as R tuple of Hilbert small point?
It's a product of so your shift will split as a direct sum of rank 1 torsion-free shifts. Yes. No, you integrate over all, but the fixed points of the framing group action would be the split shifts. I mean, it's just all right. So this is what we want to do, and in fact, there is not much you need. Okay, let me take as an example. So this is example, and this is a special example, but it's connected more directly to what we are doing here. So let me take the group to be ZR plus 2. Apologize for strange notation. So it acts by Z3, Z4 going to omega is the primitive root of unity. And now we just, okay, so now I also need to explain, so my framing space. So what you probably have also inferred from Andre's talk was that this n rank n shifts, they sort of correspond to doing something on the kind of fattening of this plane, and this fattening is of kind of length n. So if you try to think geometrically about what this rank n shift describes, they describe kind of surfaces with multiplicity, and this multiplicity is sort of spread out in this transverse direction. So these n guys, guys, they actually look like so what I'm trying to say is that you should think of this rank n as sort of corresponding to n points, kind of n points dancing on this transverse plane. Okay. And now that I have the group action, and the group acts on this plane, well, it might act on those points somehow. And so we want to, so there are different ways of different group actions depending on how this group acts on the collection of those points. And so one kind of, again, the simplest way to let the group act is to say that these points actually form orbits of this group. And so in the sense that you say that this is the space of kind of functions on n, so this is boldface n. This is the number n on n copies of gamma orbits. In other words, I'm trying to represent something which on the quotient space, and the quotient is actually, well, it's a singular space. So this is the C234 divided by gamma. We discussed those quotients for r equals to 0 at one of the previous lectures. But so again, we can. So if you introduce the invariance, I'll change notations. That as an algebraic manifold, this is just a surface described by the equations AB equals C to the power R plus 2. Wait. So I just want to say that on this quotient space, I have n points. Okay. So n points here. And each point on the quotient space, unless it sits at the singularity itself, will lead to an orbit. So this is one orbit. This is another orbit, and so on. So on the covering space, it means that I have n times r plus 2 rank n times r plus 2 sheaf with gamma action. Yes, what's the question? So you see, okay, these are sheaves on C2. But what I'm trying to describe a kind of a fiber. The fiber of the sheaf should be viewed as a space of complex functions on a zero-dimensional scheme on the transfer space. Yes. Right. So somewhere in the sky there is the rank 1 sheaf, and we push it forward down. Well, yeah. So because of n copies, but
Can I understand? So if you have rank n sheaf on the surface, are you saying that this is a torsion sheaf on fractal or?
yes.
But this torsion sheaf is only
It's a torsion-free. It's a torsion sheaf on this four-dimensional space.
It is still set theoretically supported on that basis.
Yes.
But okay, but then that's not exactly supported everywhere on that file. It's just set theoretically is still supported on C. You can't go so far in the file.
No. Of course, this is all infinitesimal picture, so to speak. I'm just trying. Yeah. We have. I mean, this is getting inside the meat of the problem. Of course, there are. We're not just counting sheaves. We have sheaves, and we have sections of adjoint bundle twisted by this normal bundle. So in principle, there is room for actually going, finite distance in this space. That just question whether you have solutions where the Higgs field has non-trivial value. Just since we work equivariantly with respect to many symmetries, including the torus which acts on that space, we actually cannot move anywhere outside this point because of the torus symmetry. But if you remove this symmetry, then you can go all the way. Okay, so all this is to say that the space n, and its character, will now split as a sum over both the colors which we had before and the new object which is the representation which is the irreducible representation of the group gamma. So the group gamma, being cyclic group, has a ring of representations which is generated by one-dimensional reducible representations. So let me just call it like that. So R0, R plus 1. So these are irreps where the generator of the cyclic group acts by its S power. So S goes from 0 to R plus 1. And so I just, for each representation, for each reducible representation, I have an n-dimensional sheaf. So I have an I have an n-dimensional vector space, which will be the fiber of the trivialization of my sheaf at infinity in that space. And these are now equivalent parameters for the framing group acting there. So the framing group is now GLN to the power R plus 2. So for each irreducible representation of my group gamma, I have its own framing. And so if you formulated the problem of doing instanton counting as an integral of, is it Reith product? Maybe it is a Reith product, yes. These are actually invariants. So for me this is the so this is the subgroup of the huge framing group, which commutes with the group Z. It's not a Reith product. Okay, so the modular space of now let's call them Quiver instantons. It's just it's the ZR plus 2 invariant locus in the derived modular space of framed rank LR plus 2 sheaves on P2 with trivialization over P1 at infinity. And now this trivialization involves, so the trivialization is now includes the group, the decomposition of the fiber at infinity as a representation in irreducible representations of the group gamma. And my requirement here is that the ranks of the isotypical components are all equal to n. So that's this is what it means to be a regular sheaf. Now the new phenomenon is that well, basically it means that it's just a collection of torsion-free sheaves. So EI is torsion-free on P2. It is trivialized, sorry, ES it is trivialized over P1 at infinity. And what else? So they all have ranks equal to n, and they have, but they can have different Chern classes. And so this space is the disjoint union over now the vectors of instanton charges. And so in doing the counting, we will be summing over these charges with new parameters. And that's the proliferation of the coupling constants, which we also saw in this example. So it means that what used to be the single Q will now become a collection of Q0, QR plus 1. And so we'll have the Z function and other functions which are now collections of, so the arguments are now all of these covariant parameters, the vector of Q couplings, but we still have the three parameters epsilon 1, epsilon 2, epsilon 3, because the symmetry, we still have the symmetry of rotations of this plane, and we also have a symmetry of rotation of that plane. What's so special about the cyclic group is that well, it commutes with the torus section, so we don't lose any parameters. If you take the dihedral or icosahedral or I forgot what they called. So the groups which are the Kleinian groups which correspond to the exceptional series, then they actually they will rotate Z3 and into Z4, and so we will not have the independent symmetry of with the epsilon 3 and epsilon 4 parameters. So it will we will have to impose an additional relation on epsilon 1 and epsilon 2. So that theory is slightly more complicated because of that, because they have fewer parameters to play with. But for now, let's stay within A series, and so okay, instanton here. And then we have this huge product over, oh, sorry. And of course, we'll have that now the sum over the collections of partitions, which now will be labeled by two integers, alpha and s, because for each sheaf, it will split into sum of Rankine sheaves, and they all are monomial ideal sheaves, so they're labeled by their own partitions. So these are, so it's now n times r plus 2 tuple of Young diagrams. And so the number ks is just the sum over alpha from 1 to n of the size of diagram under S. But then the measure which you put here is can be obtained, simply from the formulas which we had already by the simple rule. So you write the formula for the theory with the gauge group of that rank, and then you just keep terms of zr plus 2 charge equal to 0. So what is the charge? The charge. So again, we'll assign the charges to this parameter. So this guy will have charge s. Just read it off the index. Epsilon 1 and epsilon 2 have charge 0. Epsilon 3 has charge 1, and epsilon 4 has charge -1. So you take the expression from Wednesday. So these expressions were some linear functions of A, epsilon, and epsilons. And then you just compute the charge of the linear combination of this expression to be simply the sum in alpha s times s plus m3 minus m4 modular r plus 2. So if this is 0, then you keep this factor, and if it's not, you just throw it away. So the big gauge. So that's the. This is the thing which is hard to understand in quantum field theory, but this is what you learn in string theory course. So this is the big gauge group doesn't exist actually. It was. Yes, yes. I mean, maybe it exists in some, in this. If you add back all string excitations, so this becomes deep. This becomes D-branes. We're doing some kind of open strings, and but this orbifold projection is a projection. No, it does not exist. So the gauge group is what survives the projection. Yes. Maybe sorry, Ardan. No, of course, I'm speaking from the perspective of quantum field theory. But these days, one should speak from the perspective of condensed matter theory. And in condensed matter, gauge symmetries and all kinds of projections, they are all effective things. These are things which exist at low energy. So, for example, there is famous Kitaev toric code, which is a kind of a gauge theory. In his approach, all gauge constraints are just low energy approximations. So maybe there is some bigger theory in which. Right. No, these are so the instantons will be with this gauge group. So these are the instantons which I'm counting. Right. Of course. Yes, yes. So it's a collection of r plus 2 UN instantons, but the whole story is that these are now instantons with matter. So this word derived means that from the conventional physics point of view, it's a theory with bifundamental hypermultiplets. So they talk to each other. No. So they solve different equations. They solve this non-abelian Zabir-Quinton equations with matter fields. Well, on the localization locus, they are actually instantons. The matter fields vanish on the solutions of the equations, but the fluctuations contribute to the integral, and that's what we are discussing. Yes, that's what I'm doing. I'm just explaining Quiver gauge theory in this geometric way. Yes.
And that partition function, if you start from G, rank n over its own support, push it forward onto the support, kind of roughly what you're doing when you look at the first case locus. Then on the base C2, the rank is the same, but then you have many ways of decomposing this rank.
So when you do it carefully, and let me draw the picture which Andre alluded to. So let me just draw the picture. Maybe it will answer 1,000 questions. So the picture is the following. So we organize the representations of the group ZR plus 2 into Mackay graph. Not. So what is this graph? So the vertices are representations, R0, R1, and so on. And this is R plus 1. And the edges are decompositions of the tensor product of each representation with a two-dimensional representation, which I have defined for you. But there, this is my two-dimensional representation. So this is, so it decomposes with some multiplicities. And so these multiplicities are encoded in this graph. So of course, it's a two-dimensional representation, which is actually a sum of two one-dimensional representations. And so, so if you multiply this guy, you'll get the sum of these two. If you multiply this guy, you will get the sum of these two, and so on. And now, in doing what I did, you promote these vertices into vector spaces. And in fact, you promote them into sheaves. So they become sheaves of rank n. And so we study the modular spaces of those sheaves. But on top of those sheaves, we should think of these modular spaces of abstracted space with abstractions coming from derived homes between sheaves connected by the edges. And so that's what we're doing. So we integrate over the product of the usual modular spaces of frame sheaves. So the equivariant, I mean, again, well, some kind of elliptic class of those things. So some, and then epsilon 3 is the argument of this elliptic class. Yes, so this is called A R plus 1 hat theory. R equals minus 1 is the minimal one. It's when I do nothing. And so that's a 0 hat which we started with. So. Okay, so it looks like I'm complicating things, but I actually want to simplify things. And all this is done for the sake of illustration. And so to arrive there, let me now take the limit. So the example continued. So now I set Q0 and QR plus 1 to 0. So what it means that of this chain of sheaves, these guys are now just fixed vector spaces. So just trivial sheaves, just vector spaces. No. So okay, for the experts, for the experts, the mass of the bifundamental, which connects the nodes S and S plus 1, the fundamental field, is computed as follows. It is epsilon 3 over R plus 2 plus the difference of the U1 parts of the Coulomb parameters. So it's the sum over alpha from 1 to n, alpha S plus 1 minus A alpha S. All right. Okay, let's spend more time. So this is, why is this a simplification? Well, because then actually things start looking much simpler than they looked before. And in particular, if, let's say, R is equal to, so this gives me a R type theory. So as you can see, this is now, this part is a Dinkin diagram of a R type. And these are just some decorations. So in particular for the A1, let me just tell you what is the measure which we will get for A1 theory. So now A1 means that so I only have, so now S goes from 1 to R. This is why it was some strange choice of the group ZR plus 1. So now we have only R times N partitions to sum over. And for A1, we'll have our good old set of N partitions. And this measure will be now the product of alpha prime. And we'll have the denominator, which are the products of the partitions as before, with legs and arms. But the numerator will be now a different type of object built out of Young diagram, which follows by this projection. So this is an interesting fact about the. Okay, so what it will be? It will be A alpha minus M. So now I will introduce notation. So A0 S, which we still have, I will call M minus S, and AR plus here. So notation. A0S will be called M minus S, and A R plus 1 S plus epsilon 1 plus epsilon 2 will be called M plus S. So yeah, so you have bifundamentals for the middle nodes and fundamentals for the two. And for A1, there will be only two fundamentals. Yeah, but this is general. Right, this is general. Right. So, okay, yes, and that's what I want to say. So I'll get. So this will be the content polynomial. Times, and then the product over S from 1 to N. So these are contents of boxes. So in denominator you have arms and legs, and numerator you have contents. And so that's and you got it just by doing this general procedure. But it's much simpler. It's much simpler theory to analyze. And now to this whole picture of this beautiful world, we'll now add the Q character, QQ character. So now I will add one-dimensional object, so rank 1 sheaf extending in that direction. So this guy is no longer happy. What? So something happens at one point, and Well, for the general theory, we'll have to take the formula which I wrote, which was the sum over one partition, and project and do the orbifold projection. But now, in this simplified case, the QQ character. So first of all, sorry, I should explain one thing. So, when I say rank 1 sheaf, now because of the orbifold structure, because of the orbifold group acting on the space, I need to specify also how does it transform under the group action. And so we have, even for rank 1, we now have R plus 2 choices because the fiber at infinity can transform in one of these irreducible representations of the group. And so we have, that's why we'll have not character but characters. So they will be labeled by, so fundamental QQ characters, they will be labeled by the letter S. It will be the functions of X. And, oh my God, I need to start with the definition of the Y observable. So the Y observables also get their orbifold dress. So that's, but that's kind of easy, and that's almost, so now we'll just have, yes. You see, I have Luxapri. No, I said that we'll go back to the complicated case of A0 hat, but we need to first grow some muscles. And so we'll deal with simpler linear quiver type theories first, and then we'll go back to this. Yeah, of course, these theories also correspond to quantum integral systems. They're just not Calogera. They're Calogera with spin degrees of freedom. Okay, so first, so if I have a, so the Y observable, which was, remember, it was a sheaf, which was essentially a fiber of the tautological sheaf at this point. So now this tautological sheaf has, well, this point has an orbifold action, and so I need to specify which representation I'm taking. So let me just write the formula for you. It's the same formula we had before, but now it's I'm just a little bit refined because it has now this additional index. It is the same formula. I'm just using, so just put the index S at appropriate places. It is a little bit misleading that it is so simple. Maybe in the exercise session, we'll compute the Y observables for the in presence of the surface defect, which is a different orbifold. There you will see that it is a little bit different. It is less simple, but still straightforward. So basically, I'm just introducing the Y observables for each of these gauge groups. Very, very natural thing. So this should go like, so you could repeat the same story. We start with this observable. Its expectation values will have poles. We'll try to cancel them. Now the cancellations will depend on which instanton, so in which gauge group the instantons are sitting. And something interesting will start happening. Because now the nodes of the quiver will start talking to each other. So you see, I canceled the poles in the summation of a Young diagram corresponding to the node ES. but then I introduce the poles from s minus 1 and s plus 1. And so we'll need to close it up. Yes, yes, right. So all this, so this formula is just it's the same summation over the single Young diagram we had before, but now this Young diagram is colored, and now it is colored according to the ZR plus 2 action. So now if I draw it carefully, or try to draw it carefully, if this is Z3 and this is Z4 direction, so now the colors are according to the distance to the diagonal. So these guys, so my diagram, so the rule is the following, that you give this box color S. So this is ZR plus 2 charge S. And so all these boxes have charge S. And now in this direction Z3 grows, so this box will have charge S plus 1. So the color is blue. And these blocks will have charge S plus 2. And so the weight of the diagram, so the weight of that diagram will be Qs to the power 3, and then Qs plus 1 to the power 2, and then Qs plus 2 to the power 2. But in fact, okay, so now, because of the periodicity, if the diagram grows sufficiently far away, you may get additional contributions. But now, if I'm in the AR situation, where Q0 is equal to 0 and QR plus 1 is equal to 0, if my diagram grows too far to the right or too far to the left, its weight will be killed. Its weight will be 0. So only lambdas for which every box, so every box lambda has ZR plus 2 parity charge equals to S plus I minus J, they should be strictly above 0 and strictly less than R plus 1. So once again, the weight of the diagram is the product over all boxes in the diagram, Q with the index S plus I minus J. So this is what replaces what we had previously as Q to the size lambda. So this is the weight. And now, so I don't want Q0 or QR plus 1 appearing in this product, because that would kill the contribution. So that restricts my choice of lambdas. And so there is only a finite number of lambdas. And in fact, this finite number is equal to R plus 1 choose S. And in fact, these are fixed points in the Grassmannian, Schubert cells, or vectors in S fundamental representation. Say it again. Say. Yes. So I'm. No. So those homes, they were in the measure which I erased. So this is now something new. So this is counting in your language. So this is counting homes between this rank 1 sheaf and that and those. Yes. So these are these things. Right. Okay, so so the QQ character in this case ends up being a rather simple thing. So let me write the formula for you. So okay, remember, so by this rule, y naught of x is just a polynomial, just a product of I should have, sorry, this is the wrong notation. This is 0. This is alpha, so alpha. I apologize. And similarly, yr plus 1 of x plus epsilon 1 minus epsilon 1 minus epsilon 2 is product simply because for the nodes 0 and r plus 1, the partitions are empty. And so the boundary consists of just single box with the trivial content. And so this is what it is. So now I can write the formula. Let me introduce a shorthand notation. Epsilon without index is just epsilon 1 plus epsilon 2. And then it's a sum over all L element subsets of the set containing 0 to nr plus 1. And this is the product from B from 1 to L, Z I, let me write like that, lambda I B B. Okay. Where I introduced, again, so I apologize, I have to introduce a little bit of notation. So lambda I of x is zi times yi plus 1 over I from 0 to r plus 1, and zi is z0 times q1 qi. So this is some excessive notation, but it is convenient for calculations. So if you ever looked at Frenkel-Reshetykhin paper on Q characters, you would start recognizing something. Okay, so lambdas are kind of quantum eigenvalues of something. And where are my notes? My notes. Okay, made a mistake. Minus L. So it looks like it looks like you're doing some kind of symmetric functions of these eigenvalues, but the arguments are shifted from time to time. So this is a little bit of non-commutativity going on here. So now let me do a very, very fast forward. How much time do I have? Okay, super fast forward. Say some keywords. Let's take epsilon 1, epsilon 2 going to 0 limit. So then it turns out that in this limit, the expectation values which we were computing, which we were discussing, and so on, they factorize. So I'm talking about properly normalized expectation values. So this is 1 over in this limit. This is in this limit. So this is called the limit shape phenomenon. And so it goes back to Vershak and Kerov, Logan and Shep from the 70s. And the main importance of this limit for us is that, on the one hand, I told you that the expectation values of the QQ characters before taking limit, they were analytic functions of x, have no poles in x. Yet, by inspection of this expression, you can see that, let's say, in cohomological theory, well, in any theory, actually, so it has no poles, so it's a holomorphic section of some line bundle. And these expressions, they are sums of terms which are all sections of line bundles of the same degree. And so this whole thing is a holomorphic section of some line bundle, which is good. On the other hand, we can now, in this limit, we can relate this expectation value, okay, let me call it Ts of x, so some of degree n line bundle over elliptic curve. This is the elliptic curve of elliptic homology theory. On the other hand, by this factorization property, this is equal to the expectation value of the product of expectation values. And so we can sums and products of expectation values. This was before taking limit. And now we have that Ts of x is just the sum. So it's y0 of x times the elementary symmetric, so divide by the product z0, zs minus 1, times the s elementary symmetric function of this quantities lambda. So lambda 0, lambda r plus 1. So where now lambda, these are actually expectation values of so the zi. So now lambda I is the expectation value in the limit. Okay, so we now have a system of algebraic equations. So you need to start by, if you fix some polynomials or polynomials or some theta functions of degree n, and you want to recover lambdas by inverting this relation. So how to do that? Well, the simple way to do this is to compute the introduce a generating function. So let's multiply it by this product, multiply by Ts of x, and multiply by variable z inverse to the power s, and let's take the sum from 0 to r plus 1. So then this is going to be just the product y0 of x from 0 to r plus 1, 1 minus z inverse zi yi plus 1 divided by yi. So the left-hand side, let me denote it as rxz. So it's a holomorphic section of line bundle of degree n with respect to x, and it's a polynomial of degree r plus 1 with respect to z inverse. So there's some finite dimensional set of parameters which control this thing. So this is kind of algebraic object. And the set of zeros, so if I set this to 0, I'll get an algebraic curve in elliptic curve cross P1. So the elliptic curve is where X lives, and P1 is where Z lives. And what does this curve describe? It describes the sheets of this function. So Zi. That's very wise observation. So Zi's are fixed parameters. They were my coupling constants. Notice just one equation. It just has this equation has many branches. So these are branches. So I'll start using this breadboard because we are getting to closer and closer to where we want to get. And this is what we were working on with Igor Quiver. I mean, the last months when he was with us. So this is really very much in spirit of his view of many things. So if I draw this in this way, so this is X. Very good, very good. No, Z0 and Z, etc. are fixed variables. Wait. Let me draw this. Okay, so I'm drawing this now for the. Let me go to the rational limit so that I can draw things. Well, there are no good formulas in any case. Okay, let's not slow me down for the moment. Let me say something and then we can discuss. So over this point, my curve. So this is x plane. So this is infinity on the x line, and then these guys will be the points which Vanya is talking about: Z0, Z1, ZR plus 1. And now the curve is it's a set of zeros of this equation. So then it will do something. And over. Okay, maybe I should have written it another direction. Okay, what did you want to ask? There are no good formulas for y's in any case. So the formulas for y's are the solutions of an algebraic equation. Go to Galois, for good formulas for y's. Yeah, but it's as good as it gets. No, it's as good as it gets. But the point is, so which I should have said was that nevertheless the original parameters, the original variables a, which we had to fix, so they will be related to the periods. Yes. So the genus is what you want. So the genus, this curve, is the product of R times n. Well, it's a curve of so just by counting degree and using a junction formula. Okay, so you get the curve. So this is the curve. So this is the curve, and we want to say that this is a spectral curve. But it's a spectral curve of what? So we need to produce an operator for which. So my claim is that there is an operator also, such that the determinant of that operator, which depends on two variables x and z, is equal to this object here. So let's build that, and then we'll discuss the details. So to get the operator, we need to now do both things. So we combine this orbifolding which we had before, and we introduce the orbifold in the 2-4 plane. So now add surface defect. And so we add surface defect by introducing also the n orbifold. And so in a sense, we are dealing with a orbifold structure with respect to a bigger group. And so the representations of this bigger group are labeled now by 2 integers. So this circular or linear quiver structure will get an extra dimension. So now each thing will become, so this is now is Zn cyclic structure. And so on. And so that starts approaching, so that becomes, so the whole thing starts looking like a lattice model on the two-dimensional torus. But very concretely, what will happen will be that now each y observable s ys will become now a bunch of y observables. So now omega, so S labels representations of the R group, and omega labels representations of the N group. And so this guy is now, so I'm writing this, okay, so this is, and then, so this is going to be the product over all partitions of a given type, S, and here, so here the condition so this is if beta plus j minus 1 is equal to S modulo n. So this is an example of the projection. So this is delta beta plus. It means what? Means what? Sorry. Who is not zero? Oh yeah. So back to the general case. Yeah, back to general case. So I'm writing the formula for. I'm writing a microscopic formula first, and then we'll go to limit epsilon. There will be what? Well, wait a second. Okay. So now basically I can organize this rectangular collection of observables into a collection of diagonal matrices. So I will. It turns out that it is you can package everything into matrices. So I keep the index S, which is the Quiver index. And organize, okay, n minus 1. So it's a diagonal n by n matrix. Why is it a matrix? Well, because of this shift. So if you have good eyes, you will see that I have one condition in one factor and another condition which has a shift by 1 in another factor. So it turns out that the way to organize these quantities into fractional QQ character, which is now, which is what will encode the limit shape of the system, you write the product of matrices. And the matrices will have the form C hat, Z hat, y0 of x. So this is in the limit epsilon 1, epsilon 2 to 0. But the thing is that this is the similar sum. So it's a sum of the matrix product now, Z0, Z hat, S minus 1. And then it's a matrix of the QQ characters, X. And then there is a, okay, matrix product, let's see. Z. So where C, so hats stand for matrices. Hats means not everything is diagonal. So that's so far Y's are diagonal, but there is one non-diagonal matrix in this business, and it generates the rest. So there is this matrix C, which is a cyclic shift with the multiplication by Z inverse at the end. So it's a matrix nth root of Z inverse. And so this little shift which you had in these formulas can be packaged in the following statement, that this matrix product, so it's a product which is ordered in some way, I think it's in that way, in that direction. So it has R plus 1 factors. The claim is that if you open brackets and decompose and reorder things, so you have so here you have this shift matrix raised to the power S. The coefficient of this object will be the collection of the QQ characters, so fractional QQ characters. So this is again a diagonal matrix whose entries are now the fractional QQ characters. And the main theorem about fractional QQ characters is that the expectation values are also regular. So Z matrix, it's a diagonal matrix again, so its entries are Zi omega, and so Zi omega plus 1 over Zi omega is Qi omega. So now that we have both Quiver and the surface defect, we have these fractional couplings in abundance. And so we parameterize them in this way. So this is regular, and so it's a holomorphic section of degree 1 bundle. And so that's the whole excitement, that it's just degree 1. So it has only one. It's degree 1 because of that. You see, by doing this Zian orbifold, I've managed to factorize my Y observable into products of something of rank 1. So more geometrically, so the Y observable without surface defect was it was a kind of fiber of the rank n sheaf, and now with the surface defect, I'm splitting into one-dimensional components. Just splitting it with the surface defect. And so this is holomorphic section of degree 1 bundle. And now I'm organizing them in this diagonal matrix. And so now this is an operator. So let me call it D hat of X and Z. And as a function of x, now we take a limit and do everything on the expectation value. So this is now expectation values. Expectation values. Expectation values. And look at what have we achieved. This is an operator valued function of x and z. As a function of x, it's a linear function. It's a section of degree 1 line bundle. As a function of z, well, it's still a polynomial of some degree, but it's built out of very simple things. So if I want to reconstruct these entries, I need to learn how to factorize a matrix into the product of matrices of the form 1 minus a shift operator. And Anton Jamai here is one of the experts on that in this business. But if you're a very simple-minded person, we just look at the solutions of the equation. This is equal to 0. Sorry. So if you solve this equation, well, it's a matrix product, so one of the factors will have to annihilate this guy, and so you can actually recover the entries from the eigenfunction. So if you know the if you know the kernel of this operator, you will recover eventually these guys. There's a bit of course of a story of how to deal with the multivariateness and so on, and I will not get into that. So what's the relation of that? So just I'm almost finished with this part of the story. What's the relation of this matrix equation with this equation? That's the relation. Okay, let's now let's get no. We get Lux operator without. This is the relation. So the relation is this one. This is the relation. If you take the determinant of this operator, the right-hand side or left-hand side, the left-hand side will be the product of determinants. And then simple fact about the products of shift matrix and diagonal matrix. If A is a diagonal matrix, then the determinant of this guy is simply 1 minus the inverse determinant of A. We can do it in exercises. So the determinant will factorize, and long and behold, these y's without hat are just the products of the fractional y's. So these are just determinants of the y's with hats. And also zi's are determinants of capital Zi hats and so on and so forth. So if my determinant vanishes, which is where my spherical curve sits, then this operator has a kernel, and so then I can play this game of solving for these y's. Now, where is the Lux operator? This is not yet the Lux operator of the form we understand. Let me do it in the rational case, and I'll leave it to you as an exercise to do it in the elliptic case. It's not, it should not be that difficult. In the rational case, because D is a degree 1 polynomial in X, there's a general formula for degree 1 polynomials, right? So this is X times D0 of Z plus D1 of Z. Now, D0 of Z is actually a very simple thing. In order to extract D0, we just need to take a limit when X goes to infinity. And the only way we can get something linear in X is that we extract X from here, and here we just replace them by unity. So D0 is simply the product of 1 minus C hat Zi hat. So we can write this as d0 of z times x minus L hat of z, where L hat of z will be now the locus operator, which is d0 z inverse d1 of z. So now this object has singularities in the z variable, because by this formula, the determinant of d0 of z is simply 1 minus z inverse zi. So singularities, so the poles, so poles of L of z are at z equals z0, z1, zr plus 1. And therefore, so we can rewrite it as a sum with some residues. And because of the nature of this operator, the residues will be rank 1 matrices. Simply, why they are rank 1? That's simply because, well, when you invert an operator, which is a polynomial in Z, the residues, so the poles are at the zeros of the determinant, and the residues are essentially the projections on the kernel and of the kernel of a dual operator. Li hat depend on everything. The L hat depend on Z hat, and if you like, yeah, maybe you can organize them into A's. Yeah. So they contain information both about the theory without surface defect, which from the point of view of integrable system are integrals of motion, and but they have twice as much information in there, because the surface defect brings the data of these ZIs, which are not visible in the bulk theory. And so these are actually degrees of freedom which actually change in the lux flow. No. ZIs are the parameters of the surface defect. So the product of omega. Okay, so Zi hat is for each I it's n numbers. The product is fixed by the gauge coupling constant, but which leaves you with n minus 1 parameters. And so these are dynamical parameters. So that way you have n minus 1 dynamical parameters times r. And the total dimension of the phase space will be twice that. So because that also includes the integrals of motion. Okay, so now this is lux operator, and no, A's are just integrals of motion. Yes. Okay, once again, so we have A alpha S. So A alpha S. Right. So these were our parameters. So we don't get more parameters by orbifolding. Right? So how many parameters we have here? So we have n, and we have r plus. Okay. Originally we had r plus 2, but we of this r are parameters which are correspond to dynamical gauge group, plus 2 which are in masses. Okay. Now, out of its n parameters, because of this relation, the centers of masses are sent to masses. So these are dynamical, plus 1, which is the external parameter, which is the mass parameter. So you have n minus 1 times r Coulomb moduli. So these are the parameters of your theory. In fact, that should be the genus of the curve. Yes, yes. So they count. So for each of these rank n sheaves, the parabolic structure of the sheaf along the curve requires additional parameters because now the quotients can have non-trivial first-chain class. So I'm counting all of those, and these are the counting parameters. Right. Okay. So this is called. So this is going to be the Lax operator of Godin-Garnier system on genus 0 curve with r plus 3 punctures, additional punctures being at 0 and infinity. So in order to make from this Lax operator an honorable Higgs field, we multiply it by dz. And so maybe divide by z also. Multiply by, right, so the Higgs field is dz over z times this Lax operator. And I don't have time to verify that when z goes to 0, when z goes to infinity, this operator approaches the diagonal matrix whose eigenvalues are determined by the masses, by these masses. So these are the eigenvalues. So these eigenvalues of the residue of phi at 0 or infinity. So it's a Hitchin system on kind of meromorphic Hitchin system where the Higgs field has generic eigenvalues over 0 and infinity, but has rank 1 residue over the points z0, zr plus 1. Maybe I overdid it, so maybe. Oh no, it's okay. So we can scale. I mean, with the, so these guys z were defined up to overall scaling. So I can set one of them to be 1, and so then you'll be left with r parameters. Okay. All right.
Do we put some ZR plus symmetries everywhere? Spectral curve here, or
No. The symmetry has been completely. There is no symmetry. No. The symmetry was used in constructing this, but it can totally disappear. The symmetry is totally disappear. Who has what? Okay. So since LIs are rank 1, so these are rank 1, so they can be written as products. UI, when U is a vector and V is a covector, there is a symplectic structure. So these are. Okay. Very good question. Very good question. So how come? Where is the Poisson structure? So we need to think about the following: that if we take the expectation value of the surface defect, so this is the expectation. So this is the. Okay, let me just write it. So it's a surface defect expectation value. If I compute its derivative with respect to ZIS, for example. Okay, almost by definition. So first of all, if I compute the derivative with respect to Q S omega, if you normalize it properly, so that will give you the expectation value of the maybe multiplied by epsilon 1. So this is going to give me something like AS omega plus epsilon 1 as omega. So this is the expectation value of the fractional instanton charge, which you can extract from the expansion of the y observable at infinity. And in the limit, in the classical limit, epsilon 1, epsilon 2 to 0, so this psi will behave in a quasi-classical way when S depends on whatever parameters we had. So Z S omega, A S omega, and so on. And so this relation will become the relation that the derivative of S with respect to Z will give you the actually entries of U and V vectors. Now, the way to understand this relation is that this is the Hamilton-Jacobi potential which expresses the momenta through coordinates. And so this is where you can derive the symplectic structure on the residues of this Lux operator. So this enumerative geometry produces for you kind of a Lagrangian subvariety in the phase space of this integrable system, which is generic. So we describe this phase space not point by point, but Lagrangian subvariety by Lagrangian subvariety. So Z modulo the relation, which is the product is equal to the positions of these points, are the dynamical variables. So they are the coordinates on the phase space, and momenta are derived from this Lagrangian subvariety. Okay, so after we've grown the muscle with the finite A-type theory, there is a similar but slightly more complicated formula for the original A0 hat theory, which involves the infinite product in both directions, which is the kind of the matrix version of the product formula for the Jacobi theta function. And the formula for Jacobi theta function has a left-hand side and the right-hand side. And so the left-hand side will have the product of these guys, where the role of yi will be played by y hat without I, because there is only one gate group, but it's shifted by epsilon 3, and so I now becomes an integer valued. And the right-hand side will have the QQ characters, which again are shifted. So but these interesting products will contain, so they will become like Q to the quadratic function, and so this is the right-hand side of Jacobi identity, except that it's now dressed with QQ characters and matrices. Infinite product, infinite. Here it's finite because it's a finite Dynkin diagram, and for the affine case, the product will be infinite, as in Jacobi triple identity, which. Okay, we should we now call it like it's a boson fermion correspondence, right? So it's a correspondence between Fock space built on fermions and Fock space built on bosons. That's the way we prove it. Right, and you can so there are different so in this approach, Jacobi is actually A0 hat. It's not SO2. And then out of that, by again this song and dance with projections, you can get any Lie algebra. And so the analog of this d hat will be the yet another representation of the Lax operator of elliptical Legere-Moses system found by Quiver, but which keeps showing up new faces. And so as this problem, Igor's legacy is keeps going on. So I apologize for going over time.
Let's thank Nikita for wonderful. We are quite a bit over time, so I suggest that unless you have an urgent pressing question, keep the questions for the exercise and discussion sessions or for a tea break. And we still have exercises after lunch, but I think that right now we should really thank many people who were involved in organizing all the local arrangements. And in particular, I want to introduce Fan that you have seen at the reimbursement table, and also Mona. And Mona is the one who was ordering things, taking care of your many hotel requests and everything. So without them, it wouldn't go as smoothly as it did. Thank you very much. And I want to ask the two people who were instrumental in starting the conference and making sure that it will happen, Nikolai Reshetikhin and Andrei Okunkov. So,
thank you. So I have two main messages. First, I want to thank Anton for really running the show. He was absolutely instrumental for this to happen. Hello? Hello? Yes. So he was absolutely instrumental for this to happen. Second, it was great pleasure to see many young people and students. And I want to say that please come to BIMSI again. And if you are a student, we are designing the joint graduate student programs. So you can come here for a year or so, or for a few months. And if you have a co-advisor here, I think with Chiujing College from Tsinghua, we have this kind of designing the new system when there will be an advisor at Tsinghua and co-advisor here. So for all other students, you are welcome to participate in such program if you are in some other university. And if there is no such program with the other university, then we will work on this program and we will make it. Okay, thank you for coming. And Andrei.
Yes, I think it's a good message to let's have lunch now and thank everybody.